properties of equilibrium constant, okay? So the first property of equilibrium constant have already been explained, okay? Equilibrium constant can be expressed in terms of pressure and what? Concentration. It can also be expressed in terms of activity series. It can also be expressed in terms of activity series, okay? So in terms of pressure is going to be called Kp, in terms of concentration is going to be called Kc, in terms of activity series it will be called what? Ka, okay? So we can express equilibrium constants in these three expressions. That's one of the properties. Okay. Number 2 is that the value of the equilibrium constant is unique and correspond to a well-balanced equation. Okay. Just like we did in the previous videos, in the previous explanation, you cannot write the equilibrium constant without balancing the equation. Okay. A well-balanced equation is unique to the value of the equilibrium constant. Okay. Now the number 3 is that the equilibrium constant for the forward reaction is inverse. It's inverse to the equilibrium constant for the backward reaction. So Kf stands for equilibrium constant for forward reaction. Kp stands for equilibrium constant for backward reaction. So what I mean is that if I have a reaction A plus B to give us C plus D, and the equilibrium constant, let's say, is 2. If I reverse this reaction, C plus D, to give us A plus B, that is the opposite of this reaction, the new equilibrium constant will be inverse of this, which is 1/2, which is equal to what? 0.5. So if this is the equilibrium constant for this particular reaction, let's say equilibrium constant for the forward reaction, and this is the equilibrium constant for the backward reaction, the backward reactions for the same reaction will be an inverse of this guy, 1/this. So this is exactly what I mean. So the equilibrium constant for the forward reaction is equal to the inverse of the backward reaction. So if you look at it, Kf times Kb is equal to 1. And if you confirm it with this, you also see that Kf is 2. So 2 times 0.5. 0.5 will still give you 1. Okay, 0.5 is like saying 1/2. So these two can still have this. So the equilibrium constant for the forward reaction is an inverse of the backward reaction. Now the next one is the equilibrium constant. If the equilibrium reaction is multiplied by a coefficient, the new equilibrium constant would be the old one raised to the power of the what? Factor. Let me quickly explain this. Please look at this rule number 4, this property number 4. Let's say we have a reaction like this, and the equilibrium constant of this reaction is, let's say the equilibrium constant is 4. For example, I'm just making an assumption, okay? Let's say the equilibrium constant is 4. We are saying that if we now multiply this equation by 2, let's say we have 2 times A, 2A, plus 2 times B, 2B, and we have 2 times C, 2C, plus 2 times D, 2D. Let's say we multiply everybody by 2. The equilibrium constant for this new one would be this old one raised to the power of the factor, what you use multiply, which is what? 2. So the equilibrium constant will be equal to what? 4 times 4 is what? 16. That's what I mean. Let me show you another one. If I have a reaction, let's say I have nitrogen plus hydrogen to give us ammonia. Okay, let's assume that after balance, let's say this is balanced already. Remember, to balance this equation, I can put 3 here, and then this one I can put 2 here. Let's say the equilibrium constant for this reaction is, let's say it is what? 2. Let's say it is 2. If I divide everything here by 2, if I divide everybody here by 2, if I divide everybody by 2, or if I multiply everybody by half, let's multiply this equation by half. If I multiply this equation by half, or everybody by half, here will become N2 half plus half times this will give you 3/2 hydrogen. In a reversible reaction, half times 2 will give you 1. So here will be NH3. Watch carefully. This equation and this equation are balanced. The difference is that for this one, the equilibrium constant, this is balanced already on its own after placing the coefficient. But now, if I multiply everybody here by half, half times 1 is half. Half, 1 over 2 times 3 is 3 over 2. Half times 2 is 1. Okay? So, this is the new equation. So, if we got this equation by multiplying this thing by half, the new equilibrium constant for this guy would be the old one, which is 2, raised to the power of what? Half. Which is like saying equilibrium constant is equal to square root of what? Of 2. That's the equilibrium constant. Okay? So, that is exactly what you should understand about this one. If the equilibrium reaction is multiplied by a coefficient, that new equilibrium constant, which is this new one we are getting here, would be the old one, which is 2, raised to the power of that number that you use to what? Multiply, or that factor that you use, which is half for this case, which is 2 for this case. Well understood. Okay, so the next equilibrium constant, the next property we'll talk about is the second to the last one here, right? Now, equilibrium constant. The equilibrium constant for partial pressure Kp and Kc can be related using Kp is equal to Kc RT change in N. Take note, where you know this one already from what we have been doing. This is the equilibrium constant in terms of pressure, equilibrium constant in terms of concentration. The R is either going to be 0.0821. Remember the unit is atm dmq per mole per Kelvin, or you can also use 8.314 joule per mole per Kelvin. So we can only use this. Most of the calculations you are going to be solving in this course will cover you will be expected to use more of this one, okay, this one, because this one will suit the unit you are working with. Okay, remember that for you to use this one, the concentration will be in mole per dm cube, the volume will be in what? Dm cube or liter also, and the pressure must be in what? atm. The partial pressure of those gases should be in what? atm, for you to satisfy this one. But if you want to use 8.314, the pressure must be in Newton per meter square or Pascal. While the concentration will be in mole per meter cube. Okay? So this is how this is the equation that we use to solve for either Kp or Kc. Now T stands for what? Temperature. T stands for temperature, and the temperature must be in what? Kelvin. Okay? Must be in Kelvin. If it's in degrees Celsius, you convert. How do you convert? If the temperature is in degrees Celsius, that is degree C, just add 273, it will change to what? Kelvin. So if I have 20 degrees C and I say convert it to Kelvin, it's just to add 273, okay? So 273 plus this guy will give you 293, okay? Kelvin. So 293 Kelvin is the same as 20 degree C, okay? Now the last parameter is delta N. Delta N is the change in number of mole. Delta N is simply the change in number of mole of the reaction for gaseous species. This change in N, this power delta N simply means change in N simply means change in number of mole, okay, for gaseous species. So the change in N is for gaseous species. Gaseous species from the equation. For example, this is in gas, this is in gas, this is in gas. So if you are calculating change in N for this one, the change in N will be with respect to those ones that are in gaseous species. So change in N will be equal to number of mole of product minus number of mole of reactant. How many moles are in the product here, which is 2? 2 minus. How many moles are in the reactant? 3 plus 1 is what? 4. 2 minus 4 is minus 2. So change in N for this equation is minus 2. Okay? So the value that will be here, if you are using this equation to do any solving, should be minus 2. But if it's something else, if it's another equation, you have to make sure the equation is balanced first before you calculate this. And once you see any matter, any reactant or product that is not in the gaseous state, don't add the coefficient or don't add the number of mole in your calculation. Ignore it. What I mean is this: if I have, let's say I have calcium carbonate decomposing to calcium oxide plus CO2, okay? This is solid, this is solid, this is gas. First of all, is the equation balanced? Is it balanced? Yes, it is balanced. Now let's solve delta n of this equation. The delta n of this equation will simply be, this is solid, ignore this. How many mole is here? 1 mole. This is a gas. So product is going to be 1 minus 0, which is equal to what? 1. So change in n for this particular one, for this particular equation is 1. But change in n for this equation is minus 2. Take note. So by the time you get that value, you can now plug this value here and then solve for any parameter that you are looking for in the equation. So Kp and Kc are related using this expression. Now the last equation is this. The last property or the last feature of equilibrium constant is this. Okay? The equilibrium constant for the activity series can be related to the what? To the standard Gibbs free energy. Okay? Can be related to the standard Gibbs free. So the standard Gibbs free energy is equal to minus RT natural log of Ka, which is the equilibrium constant for the activity series. Okay? So the R here usually is 8.314 only. You can use this one. Use this one. Joules per mole per Kelvin. Okay? So the delta G is being the Gibbs free energy. Delta G simply means Gibbs free energy. Okay? You can say standard Gibbs free energy. Now you know what the Gibbs free energy does. What the importance of the Gibbs free energy. If you can be able to calculate the Gibbs free energy of a reaction, you can be able to predict if the reaction will be spontaneous or non-spontaneous. Okay? If it is negative, then the reaction will be what? A spontaneous reaction. Okay? So this equation will help us to determine if the reaction is spontaneous and also help us to evaluate the equilibrium constant for this activity series. Given if you know the Gibbs free energy, you can be able to evaluate this. Okay? Why T is for temperature. Okay? T stands for temperature in Kelvin. In Kelvin, take note. Okay? T stands for temperature in Kelvin. So with these informations, there are so many questions you can attempt using this port information. So we're going to look at some calculations, just 1 or 2 calculations that will help us to understand this equation here and also this equation here.